So I'm very happy to present the Aws group. I'm the first person over there, Aws. And we work on programming languages. We have famous people like Tom Rapson and Somesh Jha, and young and ambitious people like Aws Albarghouthi and Justin Su. In fact, so ambitious that if you, again, look at the CS Rankings website that aggregates publications in top-tier venues, and you look at the past 8 years in logic and programming languages, the areas that we've been actively working in, and the period that we've been, our young faculty have been working through, we are ahead of Carnegie Mellon University and MIT, which have been historically the main players in this field. So pretty exciting times for programming languages in our department. So what do we do in this programming languages business? There are so many developers out there. Estimated numbers are like 18 million and growing. Everyone wants to become a developer. Everyone wants to write code. So, and the size of the code that is out there is increasing at an exponential pace. Everything is software. We all have phones that are currently running and doing things. Maybe recording even this lecture and sending it to someone that we don't even know. Okay. So if you look at original old school software like Photoshop 1.0 and Unix 1.0, we're talking about a few thousand lines of code. And now if you look at the scale of Google, it's billions and billions of lines of code that is critical for our infrastructure, whether we like it or not. So any bug at this scale can manifest and affect a lot of lives and a lot of people. So there are all sorts of bugs that can happen. There are classic bugs that people have studied intensely in our field, like the Ariane disaster, where a rocket exploded. Recently, there's been security vulnerabilities that have affected millions, including the heartbleed bug, and so on. So how do we deal with those? And the problem is even exacerbated recently. For example, not only are these bugs affecting people in terms of losing money and killing people, but they're affecting their lives in more nuanced ways. For example, algorithms that are making decisions can be racist and sexist and biased against different kinds of people. So that's a major problem, and this is something that in the past we did not anticipate, and these are the kinds of vulnerabilities and problems that we have to face right now and face in the future again and again. There are also issues with things like facial recognition, and that is growing. Like if you have your iPhone and you want to unlock it, you can just look at it. It looks at you and decides it's you, and it unlocks. And this is a simple example from a recent paper where you get Reese Witherspoon, you add some glass frames to her, and then it thinks it's Russell Crowe. So you can imagine things like this. And this class of bugs is new. We don't even know what to do with it at this point. So the solution is, of course, get rid of software. The English department is looking for graduate students. They just go down the street, and it's all solved, right? So we have a more optimistic view of this problem, the MATBL group. So we're looking at questions of program analysis, verification, and synthesis. So what does that mean? Analysis means looking at a piece of code and interrogating it, asking questions about it. Verifying means ensuring, by constructing proofs, that these programs behave as they're supposed to behave, like they don't have any bugs, they're not biased, they do not suffer from these authentication vulnerabilities and so on. And synthesis is a more ambitious, perhaps, question of actually constructing the software automatically. Okay? So as we go forward, we envision that more and more software will be produced automatically, and we're starting to see that in many different guises these days. So less and less people writing the software, more and more software will be constructed. And how do we make sure that this software is good? It's not doing any harm. So now what I'm going to do is I'm going to talk about some of these projects along these three different lines that our faculty are doing. So this is work from Loris D'Antoni, who's looking at the problem of program synthesis. Again, generating software automatically. So essentially the developer, or any person really, can say, okay, I want a piece of code that organizes student meetings for the Welcome Week. Okay, so you've all been assigned meetings. This was done meticulously by hand, but you can imagine a piece of software doing this job. So I can say, give me a piece of software that organizes student meetings where someone gets to meet with their most, the area that they're most interested in. So program synthesis searches the huge space of programs. There's infinitely many possible programs, of course, and gives you one such solution. But of course, not only do you want any program, you want something that is fast and performant, for instance, so you can give it more objectives, saying not only do I want a program that assigns students to meetings, but also the program is really fast because I want to run it and I want to get the schedule before the students show up on Friday. Right? So Loris has been working in this space and applying this problem, this approach to many different areas, including the networking work that Suman had mentioned together with Aditya Akela. So in that space, there's huge networks like in data centers, and people, network administrators work really hard to make sure the network is not vulnerable. All the kinds of information is flowing in the right places. There's firewalls. People don't access parts of the network that they're not supposed to access, and so on. So it's a lot of low-level coding. And what Aditya and Loris have been doing is allowing people to state the high-level objectives and then generating code automatically that does this incredibly meticulous work automatically and in a correct fashion. Okay. So this is another instance of program synthesis that we see. In work with Loris, we've been looking at the problem of bias in programs. Okay, so these programs can be written by hand, like a set of rules that say they decide whether to give someone a loan or deny them a loan. For instance, admit them to graduate school or not admit them. We do not use an algorithm, but I'm just saying, if more and more of you start applying, at some point we might have to. So we're looking at questions of how do we make sure that these algorithms are fair? How can I prove to you that this algorithm is fair or unbiased? For some definition of the word. And if we detect these algorithms in the wild, can we fix them? Can we fix these algorithms automatically? Can we patch them up and make them fair? And at the same time, as more and more decisions are being made in a large and distributed fashion, how can we monitor these algorithms as they are running and make sure they're not doing anything pernicious, they're not affecting people, they're not harming them? So these are questions that we've been looking at, and I think it's a very exciting problem for programming languages researchers. How do we deal with such programs and how do we deal with such nuanced properties? In another problem that I've been working on with Justin Su, we're looking at the question of privacy. Right now, if you have an Android or an Apple phone, it is probably sending data to Apple or Google or maybe even third parties because of your apps that you've installed. And these companies are analyzing this data and making some statistics and deciding how you use your phone and so on. And all of these analyses can leak your private information. So there's been a lot of work on avoiding this leakage of private information in traditional data analysis by adding noise, and this is to the analysis, and this is known as differential privacy. So if you have an Apple phone or you use something like Google Chrome, a lot of your data is noised to avoid detecting that it's you who sent that data. Okay, so this is even implemented in the US Census Bureau. So in the next US Census, which is the large-scale population survey, they're applying this technology to avoid leaking private information so that when they release the results of the census, it doesn't show your salary no one can infer your salary or where you live or whatever personal detail that you don't want released. The issue is that these algorithms are incredibly hard to write, and you have to hire theoretical computer scientists to sit down and write them and prove that they are correct and indeed are safe and not leak information. And what we've been working on a radical approach to say, okay, let's forget about everything. Let's just generate these algorithms automatically and prove them correct, so we construct the proof of these algorithms and these algorithms correctly, instead of using very highly trained individuals who may actually end up making errors in their analysis and in the construction of these algorithms. So similarly, in a similar vein, Justin has been working on verifying randomized or probabilistic programs. So a lot of the programs that we're using these days are randomized. Okay? So if you've trained any machine learning model, chances are you've used a randomized algorithm like stochastic gradient descent. And these algorithms have interesting behaviors because at any point, you never know what results will they give you. Will they give you a good result? And what Justin has been doing is taking ideas from theoretical computer science and bringing them into programming languages in order to answer questions about how accurate are these algorithms, are they stable, do they generalize to other data sets, and so on and so forth. So very interesting work taking theory and applying it in a more practical and more mechanical setting. Similarly, I've been working with Sonia on the question of training neural networks to understand code and perhaps generate code. Okay. So we have tons of code out there. If you go to GitHub and you search, you can produce almost an infinite amount of code that people have written. And we have neural networks which are really powerful and can understand text and produce text. You've probably seen many instances of neural networks generating complete articles, news articles and reviews and so on. So can we do the same thing for code? And can we train the neural network to understand code? And can we ask it, what exactly do you understand? And of course, when we teach students to code, we help them focus on the right portions of the program that affect its meaning and affect its behavior, okay? Like while loops and if statements and so on. So we've been working on approaches to understand how these neural networks behave depending on how you train them. Okay? So you want to train them in a way that you convey the right amount of information. So on the right, what you see is that in a technique that we developed, the neural network focuses more on language keywords and variable names and operators instead of on parentheses and squigglies and semicolons and things that do not convey so much meaning. Okay? So that's what we've been working on. So in a different direction, Tom Reps has been doing something quite radical of taking Newton's method, which you've probably seen maybe even in high school or in numerical analysis class, which is a way to find the root of a function that dates all the way back to Newton, and you simply take a function like this, and you take derivatives, and you draw these tangents, and you follow the tangents all the way to the root. And it turns out if you want to analyze a program, you can apply the same techniques by viewing the program as if it's a function and taking derivatives of a program. Okay? So it's a very exciting approach for program analysis, and it helps you answer questions like, is there a bug? Can you find me a bug? Can you find a proof that there is no such bug? And so on, using Newton's method. In another line of work, Somesh Jha and Tom Reps are working on deep bloating software. So whenever you use a piece of software, it usually has so many bells and whistles. Like there are so many things on my phone that I never use, so many features that come with, say, an Android or iOS that I never use. And the more things you have, the larger your application, the bigger the attack surface is. The more likely a hacker or a vulnerability will be exploited. Okay? So if I have a large piece of software and I'm only using a small piece of it, how can I reduce the scope of this piece of software to only the piece that I'm interested in? So here, for example, we have a gigantic piece of software that's using many libraries, and all of these libraries might have holes where attackers can attack. And what I want to do is just focus on the portion that is of interest to me. Okay? And of course, a lot of software is very entangled, so how do you extract the piece of code that you're really interested in is a very interesting problem. So this is just a hint of tip of the iceberg of all the things that we do in the MadPL group. But in general, our view is that software is changing. There are new tasks. There are new classes of bugs. We don't even know what they are and what they will be. But we have an indication of the fact that the world is changing. And more machines will be generating code, either using machine learning and neural networks and so on, where the code is learned automatically, or using program synthesis, where the code is, algorithms are constructed automatically. And this is an exciting time to be in computer science and programming languages. And the focus of this group is on automating programming, using, for example, program synthesis, and making sure that programs are reliable using program analysis and verification by inspecting programs and interrogating them and proving them correct automatically. So, welcome, and thank you for coming, and I hope to see you here in September.